Hey, welcome. So today, we're going to talk about thermal cameras. These amazing gadgets that let us see the whole invisible world of heat that's all around us. They are seriously powerful tools, right? From home inspections to search and rescue. But what happens when the camera shows you something that just completely defies logic? Okay, let's get right into it.
So, take a look at this. We've got a hot pan here. It is clearly sizzling hot. But when you look at it through the thermal camera, that shiny surface, well, it looks cold. How is that possible? A hot object showing up as cold? I promise, this isn't a trick. It's actually a puzzle that reveals a deep truth about how these cameras really work. And it's something every single person who uses one has to understand. So, what is going on here? Your first thought is probably, is my camera broken? But no, it's working perfectly. What we're seeing is something called the thermal illusion. And to get our heads around it, we've got to touch on a really core principle of physics.
Okay, this right here is probably the biggest misunderstanding about thermal imaging. We all think the camera is like a remote control thermometer, right? But it's not. It's actually a detector for thermal radiation. This means the energy it sees is a mix of things. It's seeing the energy the object is actually giving off, but it's also seeing the energy it's reflecting from everything around it. And that right there is where things get tricky.
So, the camera can't tell the difference between the energy an object is emitting and the energy it's reflecting. This is its big blind spot. And to get you an accurate temperature reading, the camera actually needs your help. You have to give it some clues about the surface it's looking at. Because, as we're about to see, not all surfaces play by the same rules when it comes to radiating heat.
And the magic property that governs all of this is called emissivity. The best way to think about it is it's a material's honesty in reporting its own heat. We measure it on a simple scale, from 0 to 1. A perfect emitter, something scientists call a black body, has an emissivity of 1.0. It's perfectly honest. It radiates all of its heat, holding nothing back. On the flip side, something with an emissivity of 0 is a perfect reflector. And here's the kicker. It all comes down to this super simple but really powerful relationship, which is a version of something called Kirchhoff's law. For any solid object, its emissivity plus its reflectivity equals 1. That's it. What this means is a surface can't be good at both emitting and reflecting. It's a trade-off. If it's a terrible emitter, it has to be a fantastic reflector.
And this just nails the point perfectly. Look at this comparison. On one side, you have something with high emissivity, like simple matte black tape. It's a fantastic emitter. It tells the thermal truth. But then you look at the other side, a surface with low emissivity, like our shiny pan or this polished aluminum. It's a terrible emitter. It's basically a thermal mirror. And that's the whole secret. The camera isn't seeing the pan's real heat. It's seeing a reflection of the cooler room around it. That's why it looks cold.
Okay, so if the camera can be so easily fooled by reflections, how in the world do we get an accurate reading? Well, the answer is we have to step in. We have to give the camera two critical numbers about what it's looking at.
So here are your two jobs. First, you have to tell the camera the emissivity of the target. Is it brick? Is it skin? Is it polished steel? They're all different. And second, you have to tell it the temperature of the surroundings that are being reflected. We call this the reflected apparent temperature. If you don't give the camera these two numbers, it's just making a wild guess.
And if you're not convinced this is a big deal, just look at this table. The difference is absolutely staggering. If you're measuring brick, which has a really high emissivity, and you're off by a little bit in your settings, your temperature reading is only off by maybe a degree or two. No big deal. But look at the polished aluminum. That exact same mistake in your settings creates a massive error. We're talking over 20 degrees. This is why getting emissivity right isn't just a nice to have, it's absolutely critical for accuracy.
All right, so we get the problem. Now for the good part, how do we actually solve this out in the field? Well, the pros have a couple of really simple but kind of brilliant tricks up their sleeves. The first and most common trick is to just create a spot you know you can trust. It's so easy. You just take a small piece of high emissivity material, like plain old matte electrical tape, and stick it on that shiny surface. You wait a moment for the tape to reach the same temperature as the object, and then you set your camera's emissivity setting to 0.95 and measure the tape. And boom, just like that, you have the object's true surface temperature. You've basically created your own little virtual black body.
But what about that second number, the reflected temperature? For this, you use another super simple tool, a crumpled up piece of aluminum foil. Because the foil is such a terrible emitter, it's an almost perfect thermal mirror. When you aim your camera at it, you're not seeing the foil's temperature at all. You're seeing the average temperature of everything in the room that's being reflected by the foil. And that reading, that's your reflected apparent temperature, or TREF.
Okay, so once you've got those two techniques down, there's one more secret, a workflow secret really, that separates the amateurs from the pros, especially when you're out there capturing really complex scenes with lots of different materials.
Now, this is going to sound completely backwards after everything we've just talked about, but trust me on this. When you are out in the field capturing your images, you should set your camera's emissivity to 1.0.
So why on earth would we do that? Well, this quote really nails it. When you set the emissivity to 1.0, you're basically telling the camera, hey, don't try to calculate anything right now. Just record all the raw thermal energy you see without making any assumptions. You're capturing the pure, unedited radiometric data.
And the payoff for doing this is huge. It preserves all that raw data, so you don't bake any errors into the image while you're on site. This gives you all the power later. You can go back to your computer, open the image in your software, and then assign the correct emissivity and reflected temperature to different parts of the image. You can analyze the metal beam and the concrete wall right next to it, each with their own correct settings. It's the key to doing flexible, accurate, and defensible work.
So, that cold hot pan, it wasn't a glitch. It was a physics lesson. And by understanding emissivity, you're not just taking a thermal picture anymore, you're actually conducting a scientific measurement. You've unlocked the secret to making your camera tell you the truth. So, the only question left is, what are you going to discover?